So back over here on this page, so it's critical value. So critical value, some books call them critical numbers. They are very important. They are basically, a critical value is where a max or min might occur. Where a max or min might occur. It's the only place, actually, I'm going to add that. It is the only place a max or min might occur. So when you find a critical value, that's not a guarantee that you'll have a maximum or minimum there, but if there are maximums or minimums, critical values are the only place it could happen. The only place. Okay? So to find a critical value, I'm going to actually start here. You look at two things, two places to find a critical value. You want to know where the derivative equals 0, and you also want to know where the derivative does not exist. Just so that doesn't freak you out there. The derivative does not exist. That's basically asking about the domain of the derivative. Like, what would cause the denominator to be 0, or even rooted radicals, or stuff like that. So you check these two things, and these two things will produce critical values. But just because they produce some numbers doesn't automatically make them critical values. Once you get numbers produced from these two things, you've got to go then back to number 1 here and say, are these really critical values? Meaning, are they in the domain of the original function? If yes, if they're in the domain of the original function, then they are critical values and you may proceed. Okay? If they're not in the domain of the original function, they are not critical values, and so you do not go on. So maximum, minimum, these are called local or relative extremum, depending on the book you look at. Local extrema, extremum, relative extrema, local minima, minimum, min, whatever you want to call it. So we got a function going on. Every time you have like a mountain peak here, that's a maximum. It goes up on the left and down on the right. So we have two local maximums here and a local minimum here because it goes down and then up. Okay. So we're going to be finding our critical values, and then we're going to be applying the first derivative test to those, which I will kind of explain as I go along. So I'm going to go ahead and scroll down to number 6 here. Right above number 6 or somewhere. Yep. I'm going to remind you of the Cinderella story. So Cinderella is our favorite child. We don't call her Cinderella though. She has a much cooler name, f of x. And we care everything about her. Increasing, decreasing, happy, sad. She has 2 ugly stepsisters. Don't like them. All we care, are they positive or negative? That's it. And for 13.1, 13.2, we are only talking about the top part of the story here. Okay? So, since the first derivative tells us things about our original function, the first derivative, and all questions are about our favorite original function. The first derivative actually tells us 5 things about our original function. It gives us any critical values we might need to find. It tells us if our original function is increasing. It tells us if it's decreasing. And since it tells us increasing and decreasing, then it also tells us if there's a maximum, which means you increase then decrease. And it also tells us if there's minimums, decrease and increase. So the first derivative tells us 5 things about our favorite original function. Okay. So when you're going along and you're doing problems like this one, and you start reading let f of x equals blah, 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 and you're like, I don't even know what this problem's about, and then you start reading it, when it's critical values increasing, decreasing, instantly you should think, we can get all that information from the first derivative, who we don't care about, but she will tell us all this information about our favorite child. Okay. So we know we need to do the first derivative test. Essentially, I'm going to write out the steps. Essentially, the first derivative test always begins with find the domain of the original function. That's where you always want to start. It won't tell you, but you need to find the domain of the original function. So right here is our original function. So looking for the domain, I'm looking for issues like denominators. We don't have those even-rooted radicals, logarithms. We don't have any of those. What kind of function is this? Anybody? Starts with a P and it rhymes with polynomial. Polynomial, good job. It's a polynomial. Polynomial functions are continuous everywhere. We don't ever have to worry about domain for them. So the domain is all real numbers. Okay, so mark that however you want. It's just for you to know. But it'll be important. And then the second thing we're going to do, we need to find where the derivative equals 0 and where the derivative does not exist. That's our next step. In order to find those two things, we actually need to find the derivative. So I'm going to take the derivative here. And I have 3 times negative 2 is negative 6x squared plus 2 times 3 is plus 6x plus 120. This is my derivative. And I want to look at two things. I want to know where does it equal 0 and where does it not exist. So I'm going to start with where does it not exist? Because it exists everywhere, because it too is a polynomial. There's no domain issues. So since it exists everywhere, then out of the two things that produce critical values, the does not exist one isn't going to help us on this particular problem. It exists everywhere. The domain is good. So I'll have to use the other one, which says set it equal to 0 and solve. So I'm going to set this equal to 0. And then this is where you have your choice of how to solve this quadratic. You can factor, quadratic function, use your calculator, find whatever you need to do. I'm going to pull a negative 6 out of it, and I'm left with x squared minus x minus 20. And then I'm going to factor. And so x squared is going to be x and x. I'll look at the sign right before my constant. If it's negative, that means I have opposite signs. So one's positive, one's negative. Factors of 20, that multiply to give me 20, add to give me negative 1. It's going to be negative 5, positive 4. And so I have this product equal to 0. Well, negative 6 does not equal 0. X plus 4 could equal 0 if x were negative 4. And x minus 5 equals 0 if x were 5. And so I came out with two numbers here. X equals negative 4 and x equals 5. I cannot immediately assume they're critical values though. When you come out with numbers doing these two methods, you then ask yourself, are these really critical values? And in order to answer yourself, you check the domain of the original function. All real numbers. So negative 4 and 5 are in the domain. So I can now confirm, yes, these are critical values. All right, and then step number 3. We are going to put the critical values and test numbers on number line. So I'm going to draw a number line here. And my critical values, I'm going to draw a little lower. So as I draw my number line, I've taught this class 1,000 years, which is amazing because I'm only 29 years old. But I've taught it 1,000 years, and trust me when I say, make your tick marks for the number line more like brick walls, okay? And then when you put your critical values on there, put a box or something around them so we know those are the important numbers, not the other ones. I'll explain why as we do this. So I made my tick marks like extremely tall. and I boxed my critical values. Now I'm going to pick numbers to test. So I pick numbers to the left and right to test. So the numbers to the left of -4, anything, I'll just go with -5. Between -4 and 5, I'll go with 0. And to the right of 5, I'll go with 6. I want to test these numbers in the first derivative. I want to test these numbers in the first derivative. And according to our Cinderella story up here, what is the only thing we care about in the first derivative?
Well, it's positive or negative.
Positive, negative. So when I test them in the first derivative, all I care about, did they come out positive or did they come out negative? That's it. That's all I care about. Okay? And let me tell you why you don't want to plug them back into the original function yet. Okay? So the original function is our favorite function, yes? Yes, in case y'all haven't noticed that. Formerly known as Cinderella, currently known as f of x, yes? Okay, so we don't test these numbers in the original function because only amazing things would come out of the original function. If you're going on a treasure hunt, what marks the spot?
X.
X. Is X the actual treasure? No. X tells you where to find the treasure, but it's not the treasure itself, right? So as we're doing these things and we're finding these X values, which are our critical numbers, those X values are not the actual treasure. They're not the actual maximums and minimums. We find the treasure, the maximums and minimums, by plugging things back into the original function. And so right here I'm going to say plug X values into original function to get Y values. And the Y values are basically the treasure. The Y values are the actual max and min. The actual max and min. It's a little side note that we'll be coming back to many, many times. Okay, so we want to test these in the first derivative, which I boxed, but I'll also highlight right there. So anytime you have to test multiple numbers in the same function, the quickest way to do this is use your calculator. Use your table on your calculator. So this is a great time to pull out your calculators. And we're going to put we're testing it in the first derivative. So we're going to go to y equals, and we're going to put that first derivative into y1. Alright, so I got my first derivative in y1. Just to make sure your table settings are still how we want them to be, this one time go to second window and underneath independent, make sure it's on ask. If not, move over there and hit enter. Okay, now we're going to go to the table. So second graph, if you have stuff in there like I do, just hit the delete button until everything's gone. And then we're going to type in these in green here. So -5, 0, and 6. And we came out with -60, 120, -60. But we don't actually care about the numbers themselves. All we care about is they came out negative, positive, negative. That's all we care. So we got negative, positive, negative. And according to our Cinderella story, that tells us if it's negative, that means our function was decreasing. If it's positive, our function was increasing. And if it's negative, our function is decreasing. So hence the brick walls of a tick mark going on here, because I have had students do this, and they're like, oh, look, it's increasing, and you have that 6 sitting there, so people think, oh, it's increasing to 6, so you start to confuse yourself. So I want your tick marks to be brick walls so you know when to start, when to stop. Okay? And I want you to have the -4 and 5 boxed so that you don't accidentally think these little test numbers are important. They're not. So once we have these drawn, then you can more easily see that this function is decreasing in 2 places. And it's increasing in 1 place. So it's increasing from -4 to 5. So that's an interval. It's decreasing from -infinity to -4 and from 5 to infinity. And it's wanting to know, are there any local or relative extrema? That means max and mins. So we have a minimum happening right here because it goes down and then up. So I'm going to write that we have a min at -4 something. And then we have a max at 5 something. How do we find the y values? Well, go back into our original function. That's what the original function does. It gives us y values. So the original function I have in yellow right there. So I'm just going to go to y equals real quick and type it in. This is, to me, the quickest way to do it. So -2x cubed plus 3x squared plus 120x. And then I'll go to my table. And delete. And I'm going to type in -4, enter, 5, enter. And so I get, my y values are -304 and 425. And that's as points. And just to kind of emphasize what this means that we have a min of -304, and it occurs at -4. So the min is always the y value, and it always occurs at the x value, like the treasure map. We have a max of 425, and it occurs at 5. All right. Okay, so example 7. So I'll look at what it's asking, critical values increasing, decreasing, relative extrema, and I know it's dealing with the first derivative test. So, first thing I always do, what's the very first thing I do? Find the domain of the original function. Well, this problem is different in that it doesn't actually give us the original function. It's going to ask us all these questions about a function that we don't even know. But we'll be able to answer them. So we don't even know what the original function is, but it told us the domain of f of x, right here. The domain of f of x is all real numbers except 5. So we basically, it can't be 5. Everything else is good to go. The second thing we would do is find the derivative, but they already did that for us too. This is the derivative right here. And we want to see where does that derivative equal 0 and where does the derivative not exist. Okay. So since the derivative is already found for us, we don't have to do that. A derivative is a rational number, meaning there's a numerator and a denominator. So to see where it does not exist, that's going to be where the denominator equals 0, because it's a domain thing. So I'm going to write denominator equals 0. And to see where a rational function equals 0, the whole function equal to 0, all we really care about on that is the numerator. Why is that? Because 0 over 4, that's 0. 0 over -10, that's 0. 0 over 12, that's 0. So if we just set the numerator equal to 0, then this whole function equals 0. So numerator equals 0. All right. And I'm looking at these two things where the derivative equals 0 and where the derivative does not exist because it will help me find what? What does this help me find?
F of X?
Critical values.
Critical values, critical values. Alright, so setting the numerator equal to 0, it has x minus 1 cubed and x minus 3. We don't care if there's a cube or a fifth power or fourth power or squared, because what is 0 to the third power? That's 0 times 0 times 0, which is 0, right? So we don't care what power it's being raised to. What we care about is, in the parentheses, does that equal 0? What would cause it to be 0? And so we get x equals 1 and x equals 3. So checking this one, we get x equals 1 and x equals 3. We cannot immediately conclude that there are critical values. We have to ask ourselves, are these in the domain of the original function? And the original function says everything except 5 is good. So 1 and 3, we're good. X equals 1, x equals 3. Now I'm going to check the other one. Where does the derivative not exist? That's going to be where the denominator equals 0. Again, I don't care about the squared part. I just want to know the inside. And that happens at x equals 5. I can't conclude it's a critical value yet. I have to ask myself, is it in the domain of the original function? No. Actually, it's the only number not in the domain of the original function. So it is not a critical value. However, it is important. Okay. So we just checked these two things and we came out with 3 numbers. Only 2 of them are critical values, but the third one is important. It's important enough that it appeared. It might not be a critical value, but it's going to play a role in all the other stuff. So it still has to go on the number line, even though it's not a critical value. All right, so drawing my number line out here. I've got 3 tick marks. 1, 3, 5. Underneath the 5, I'm going to write not critical value, just so I remember. Because if for some reason we're doing this plus minus thing and it were to go like down and then up, it might look like a minimum, but it's not. Because why? Because it's not a critical value. Can't be a minimum. Okay. Picking my test numbers to the left and right, I'm going to pick 0, 2, 4, and 6. And where am I going to test these? In the derivative. You're correct. I want to test them in the derivative, and the only thing I care about the derivative is positive or negative. I don't want to put it back into the original function because what would that give me? A y value. And we don't have an original function to do that to anyway. But just kind of a re-emphasis of we're putting them in the derivative to see if we get positive or negative. So I'm going to put this derivative into my calculator. And if you got like a TI-83 calculator, then when you're plugging this in, make sure you put parentheses around the entire numerator divided by parentheses around the entire denominator. For you TI-83 people out there. TI-84 people, you have that option of doing alpha y equals, which is like a game changer there. Numerator over denominator. And you don't have to worry about the parentheses. X minus 1 third, x minus 3, x minus 5, okay. So once you get your derivative into your y equals, we are going to use our table. I'm going to go to second graph, and I'm going to delete stuff that's in there already. and then I'm gonna type in my test values, which were 0, 2, 4, and 6. And I don't care about the actual numbers that appeared. What I care about is I got a positive, a negative, a positive, and a positive. So I'm gonna write that down. I got a positive, a negative, a positive, and a positive. Right there. All right, so that means we were increasing, decreasing, increasing, increasing. So this function is increasing, and we don't even know what the function is, but we can tell information about it. It was increasing from negative infinity to 1, 3 to 5, and 5 to infinity. Very cautious over here. You don't want to say it was increasing from 3 to infinity because something's happening at 5. In this case, it is an asymptote probably. So there's an asymptote going on at 5, so it can't increase through something that doesn't exist. So when you're writing out where it's increasing, that's from negative infinity to 1, from 3 to 5, and from 5 to infinity. Like normally I prefer to put unions in between these, but your online homework prefers commas, so I'm just trying to kind of get you in the habit of commas. All right, and this one is decreasing from 1 to 3. And then it's only asking for the x values where relative extrema will occur. So we have a maximum happening around x equals 1. We have a minimum happening around x equals 3. We're not able to find the actual max and min because we'd have to have the original function to plug it back into, and we don't. So that's as good as it gets there. All right. I see the questions. It's talking about critical values increasing, decreasing. That tells me first derivative. So I know I always start off with the very first thing is I find my domain of my original function. So my original function is not a polynomial this time. It actually has a radical in it. And that's the root right there. It is an odd number, so this is an odd root radical. We only have issues if there's an even rooted radical. Odd root radicals are totally fine. So our domain is everything, all real numbers. The next thing we are going to do is to find our critical values. And all right, so critical value, the only place a maximum might occur, so we need to find where the derivative equals 0 and where the derivative does not exist. So I need to find the derivative. So I'm going to rewrite this. Instead of the cube root, I'm going to make it to the 1/3 power. Okay. Just taking the derivative, this is going to be a chain rule. I have a bunch of stuff to the 1/3 power. So the derivative is going to be 1/3, a bunch of stuff to the 1/3 minus 1, which is negative 2/3. Copy the stuff in the middle, times derivative of that stuff, which is just times 1. I'm going to clean it up a little bit before I figure stuff out. So since this has a negative exponent, I'm going to take that whole term to the denominator. My fraction in front, 1 is in the numerator, 3 is in the denominator, and then I'm moving this big term down into the denominator with it. Times 1 doesn't affect it, so here is my first derivative. And I'm looking for two things. Where does it equal 0? Where does it not exist? It is a rational function. So it's going to equal 0 wherever the numerator equals 0. Our numerator is 1. 1 will never equal 0. So that's not going to get me any critical values. Where does this derivative not exist? That's where the denominator equals 0. I don't have to worry about the 3 in front or the fact that it's raised to the 2/3 power. What I am concerned is what's going to cause the inside parentheses to be 0. And I get x equals 1. So I checked my two places and they came up with a number. But before I can conclude it's a critical value, I have to ask myself, what do I have to ask myself, Colton?
If they're in the domain.
Is it in the domain? And the domain is all real numbers. So yes, it is in the domain, and so it is a critical value. We have one critical value. That means we cannot have a max and a min. We can have one or the other or neither. Okay? I'm going to put that one number on my number line. And I'll pick test numbers to the left and the right. And I'm going to test them in the first derivative. All I care about the first derivative is, did it come out positive or negative? So I'm going to go to y equals, and I'll type in, you could do like parentheses to the 1/3, or you could go to math, and the fourth one down is the cube root. Oh wait, I'm typing it into the derivative. Focus code. The derivative's down here. Alright, so alpha y equals numerator over denominator 1/3 parentheses x minus 1 to the 2/3. Okay. Then I'm going to go to my table. And I'm going to type in my two test values, 0 and 2. I don't care that they were both 1/3 or that they were even the same thing. All I care about is one was positive and the other one was positive. So I have a positive and a positive. So that means it was increasing and increasing. So immediately I know that there's not a max or min. So down here for all local relative extrema, there's none. It's not decreasing anywhere. So never. It's also not increasing everywhere. It's not increasing through 1. Something's happening at 1. We're not sure what it is at this point, but something's happening there. So it's increasing from negative infinity to 1, and then 1 to infinity. All right. All right. Example 9. Definitely want to pay attention to this one. It is on your online homework or online quiz. So it's almost verbatim, different numbers. So right here, first thing we do is check our domain. So 4x doesn't have any issues. This has a fractional denominator. So then we have to decide, well, which one of those is the power and which one is the root. And the root is always the one on the bottom. And you can think of it as trees have roots that are in the ground. So the one that's on the bottom in the ground, that's your root. And so it's an odd root radical, which means we're good. All real numbers. Then we're going to need to find our critical values, which is the only place max or min might occur. And we do that by seeing where the derivative equals 0 and by seeing where the derivative does not exist. So I'm going to need to find my derivative. So taking the derivative of this, derivative of 4x is 4. If I multiply 4/9 times 9, I'm going to get 4 x to be 4/9 minus 1, which is negative 5/9. My derivative. I'm gonna rearrange it so I can find my stuff easier. Now, x is the only thing to the negative 5/9. The 4 is not. So x needs to go to the denominator. So here is my derivative. All right, I'm looking at two things. Where does this equal 0? Where does it not exist? Now this is not a rational function because we don't have an entire numerator over an entire denominator. It's got parts. But this one part here has a denominator. So what would cause that denominator right there to be 0? If x were 0. Yeah, don't think too hard on that. So if x were 0, that would be 0. But then I can't decide if it's a critical value until I ask myself, is it in the domain of the original function? And it is, because the domain is all real numbers. So I've got one critical value so far. I also need to check where does this derivative equal 0. So I'm going to set this derivative equal to 0. You can solve this many different ways. The way I prefer to solve it is I really dislike denominators. So I'm going to multiply every term by the denominator to get rid of it. And what that does for me, my first term becomes 4 times x to the 5/9. But my middle term, it cancels the denominator. So I just have 4. And then on the right side, I have 0 times that, which is 0. So I multiplied everything by the denominator in order to get rid of the denominator. Still solving. I'm going to subtract 4 from both sides, so I get 4x to the 5/9 equals negative 4. I'll divide both sides by 4. So I have x to the 5/9 equals negative 1. Okay, so let's talk about how we would get rid of that. If we had x to the third equals negative 1, how do we get rid of x to the third?
Square root.
Not square root, cube root. Right? We would cube root that. And cube root's the same thing as raising it to the 1/3 power. Okay? And why does that work? Well, looky there. Power to a power, you multiply. So x 3/3 is x to the 1. So we want to raise this to the reciprocal exponent. We want to flip the exponent. So it's 5/9, we want to raise it to the 9/5. What does that do for us? 5/9 times 9/5 is x to the 45/45, which is just x to the 1. So we just have x. On the right side, you can plug it in your calculator if you're not sure, but just a reminder from algebra, a negative number raised to an odd power is still a negative number. Okay? A negative number raised to an even power becomes a positive number. So it's raised to an odd power, so it's negative 1. So all that fun work, and we come out with a number that might be a critical value. So we ask ourselves, is it a critical value? Is it in the domain of the original function? And yes, the domain is all real numbers. And so we have another critical value now. So two critical values. And I'm gonna put both of them on my number line. So I've got -1 and 0. Picking numbers to the left and right, I'll pick like -2, -0.5, and 1. And I'm going to test these in the first derivative. And so I'm going to plug my derivative here into my calculator. And I get y equals 4 plus 4 divided by the 5/9. Second. Delete, and I'll type in my test values of -2, -0.5, and 1. So I get a positive, a negative, and a positive. Positive, negative, positive. So that tells me that it was increasing, decreasing, increasing. Alright, and so I have, my function is increasing from -infinity to -1, and again from 0 to infinity. It's decreasing from -1 to 0. All x values where there's local, relative, extrema, we have a maximum right there. So we have a max at x equals -1, and we have a min right here. We have a min at x equals 0. Now, if it asks for the y values, how would we find them? Plug them into the original function to get the y values. And the y values are the actual max and min. X is just where they occur. All right. Exciting times. It's asking for critical values increasing, decreasing. You know what that means. You do that first derivative test. But the very first thing we're going to do is find the domain of the original function. Looking at my original function, it does have a denominator. So what x value would cause that denominator to be 0? -2. So x cannot be -2. That's my domain. The next thing I'm going to do is find my critical values. Alright, so to find the critical values, we want to know where the derivative equals 0 and where the derivative does not exist. So I'm going to need to find my derivative. And looking at this, get warm fuzzies because we get to use the quotient rule. Quotient rule says, low d high minus high d low over the square of what's below. So taking the derivative. Low, I'm just going to write it down. D high, the derivative of the high part is 10x. Low d high. Minus. High, just going to write it down. D low is just derivative is 1. Over the square of what's below. Definitely need to simplify this before I can do anything with it. So I don't touch the denominator, but I'm going to distribute up here, and I get 10x squared plus 20x minus 5x squared. I can combine those two and end up with 5x squared plus 20x over x plus 2 squared. This is my first derivative. And it is a rational function. It's a rational function, so that'll help. Whenever I wanna see where does this rational function not exist, that's going to be where the denominator equals 0. Where does this whole thing equal 0? That's where the numerator equals 0. So I'll set my denominator equal to 0. I don't care about the squared part. And I get that happens at x equals -2. I don't decide it's a critical value until I check to make sure it's in the domain. Is it in the domain?
No.
No, it's the only thing not in the domain. So it's not a critical value, but still important. Still important enough to go on a number line. Setting my numerator equal to 0, I can pull a 5x out front, and it leaves me with x plus 4. So I have this product equal to 0. So that's either 5x equals 0 or x plus 4 equals 0. Divide both sides by 5, and I get x equals 0 and x equals -4. So this one gave me two values, x equals 0 and x equals -4. Are those critical values? Yes. The domain is everything except -2, so these are critical values. So checking the two things I need to check for, I ended up finding 3 numbers. One of them is not a critical value, the other 2 are, but all 3 of them need to go on the number line. And so I'm going to draw out my number line here. Gotta erase a little bit, running out of room. Alright, and so I'm going to have -4, -2, and 0. And -2 is not a critical value. So that means -2 cannot be a max or a min. Picking numbers to the left and right, -5, -3, -1, 1. I'm going to test these in the first derivative. Testing them in the first derivative, where all I care about is positive or negative. So I'm going to go to y equals, and I'm going to type in my first derivative over here. So I'm going to do, if you're using a TI-83, put parentheses around the numerator and denominator. I'm going to do alpha y equals numerator over denominator, and do 5x squared plus 20x, and parentheses x plus 2 squared. Then I'll go to my table, delete what I have in there, and I will type in my test values. -5, -3, -1, and 1. And I get a positive, a negative, a negative, and a positive. So that tells me my function was increasing, decreasing, decreasing, increasing. So it was increasing from -infinity to -4, and then again from 0 to infinity. It was decreasing, it's not decreasing over -2 because something's happening there. So it's decreasing from -4 to -2, then again from -2 to 0. And once all points, that means x and y, where local relative extrema occur. So we're going to have a maximum happening up there because it goes up then down. We're going to have a minimum happening here because it goes down then up. So we're going to have a max occurring at -4 something and a min occurring at 0 something. And how do we find those y values?
Plug into the image.
plug them back up here into the original equation. So I'm gonna plug in 0, somebody else can plug in the other one. So 5 times 0 squared over 2 is 0. Anybody plug in -4? -40, awesome. Alright, then number 11, it says, find all maximums and minimums for f of x below. So first thing I pay attention to is which graph am I looking at, and that is my favorite one. So I'm pretty excited about that. That means everything's the truth. So it goes along, it looks like there's a minimum here. There is, because it goes down and then up. Looks like there's a max here. There is. Looks like a min here. Looks like a max here. And this is my favorite function, so I know these are all true. So I'm going to do the min first. So we have a min of, and this is where like online homework would have a blank here. So we have a min of, and this is where the y value goes. I'm doing the first one over here. So a min of -1, and it occurs at the x value, which I'm going to go with -3.5. That's the x value. Got that one. The next min, I have a min of 2, and it occurs at 0. So again, the y value, the x value. For my maximums, you look at this max is 5 and this max is also 5. So we actually just have one max of 5. It just occurs at 2 different places. And so if this is the case on your online homework, you would say there's a max of 5 and it occurs at -2, 2.